Welcome, future secondary educators. Let's take a look in this screencast at what we mean by exponentiation, both the way we teach it to young people and the way we teach it to not quite so young people. Let's decide what we mean when we say x to the n. Well, when we say x to the n, that sort of depends on what n is, right? Like, is n a whole number? If so, it's not too bad to think about. So when we think about x to the fourth power, x to the fourth power is x times x times x times x. By the way, that's not x times itself 4 times, right? There are only 3 multiplications here. So this is not x times itself 4 times. This is 4 copies of x multiplied together. That's what we mean when we say x to the 4th, or x to the 12th, or x to the 15th, or x to any positive integer. Even x to the 0 isn't too bad, because x to the 0 is just no copies of x multiplied together, and the empty product is 1. So this is what we mean when we talk about finding some thing to a power when that power is a positive integer. So then we ask the question, what happens if n is a negative integer? Well, we want still to obey the rules we set up. So we know that x to the a times x to the b is x to the a plus b, right? We still want that to be the case, even when we change what kind of number the exponent is. X to the third times x to the second is x to the fifth. We still want that to be true when we go to negative integers. So we want it to be that x to the negative 2 times x to the positive 2 is x to the 0. We want that to happen. And we know what x to the 0 is. That's 1. And so we conclude that x to the negative 2 is 1 over x to the positive 2. And it's this idea that lays out for us that x to the n, if n is a negative integer, is defined this way. We talk about x to a negative power as being 1 over x to the positive power. And it turns out, as you lay out in the text, that this definition for negative exponents allows us to keep all the properties we like with exponents. It's still true that x to the a times x to the b is x to the a plus b. It's true that x to the c to the d is x to the cd, running off of this definition. And it's worth pausing to ensure that you know that this is true. That's worth pausing to know that. So we define x to the negative 2 to be 1 over x squared. We define x to the negative p to be 1 over x to the p, but it's not a random definition. Like, it works for a reason. So now we start asking questions like, what's x to the n if n is a rational number? So really, we're asking about x to the p over q. What does that mean? Well, we have a couple of things that we want to guide our discussion here. So take x to the 3 halves. We kind of want to make sure that x to the 3 halves is between x to the 1 and x to the 2, right? So we kind of want to make sure of that. So it's got to be between x to the 2 halves and x to the 4 halves, right? So we like for that to happen. And we want to use powers. We want to connect powers with something that's like a power. And so we start thinking about maybe roots. And we also want it to be the case that x to the 3 halves is x to the 1/2 to the 3rd power, because we still want x to the c times d to represent x to the c to the d. So really, it boils down to what are we going to mean by x to the 1/2? Because whatever that is, we'll cube it. And so where the definition comes in is that we define x to the 1/q to be the qth root of x, and by that we mean the principal qth root of x, which means that we want the real root if there is one, and if there isn't, we want the one that involves the least rotation from the positive x-axis in the complex plane. We want the principal qth root of x. We want the simplest one for us to deal with. And if we define 1/q this way, then we get to define x to the p/q as x to the 1/q to the p. It's a terrible 1/q. I'm so sorry. X to the 1/q to the p, where x to the 1/q is defined as the principal qth root of x. So when we deal with 81 to the 3/2, that's the square root of 81 cubed, that's 9 cubed, that's 729, which is certainly between 81 to the 1 and 81 to the 2. But it's not midway between 81 to the 1 and 81 to the 2. That's not how powers work. Now, our choice here is important because you're going to want to think about, is it true that if you have some real number to the p/q times some other number, same number to the s/t, is that some real number to the p/q plus s/t? Is that true? Common denominator will say. So now you've got to think about, this is the qth root of r to the p, and this is the tth root of r to the s, and this is the qth root of r to the pt plus sq. Is that? Are these the same? How do we even turn those into qth roots? But that's worth thinking through. It's worth thinking about, okay, if this is the qth root of p, then this is the qth root of r to the pt, and if this is the tth root of r to the s, it's the qth root of r to the QS, and then it's not a big jump to see how that goes. But you want to do that with the properties of exponents you're familiar with so that you can believe that they work and not just trust that somebody else said that they work. All right, I deliberately stopped short of real exponents. That's coming up in the next screencast. See you there.